My topic for this semester was unsymmetrical bending, and there are two main causes for unsymmetrical bending. To simplify it, it's either the cross section if it's asymmetrical, like an angle or some crazy looking T-beam, or like a channel if it's taken at a separate angle. Another reason is the load line. If it's at an angle with the axis of symmetry, then it'll cause unsymmetrical bending. And so that can be for a rectangular beam if it's just at an angle from the axis, but that'll also cover, for example, the channel is symmetrical horizontally, but not just straight vertically, and so if that line is placed there, even though it's straight up, and even though it is a vertical load, because it's still at an angle from the line of symmetry, it'll create the unsymmetrical bending, and it'll cause some crazy looking shapes like that are what is presented here in the pictures. So basically, I'm going to dive into steps on solving. Bottom line is that when you have unsymmetrical bending, the biggest issue that's affected is shear stress, and then I guess kind of moment once you take a step further back. And of course, shear stress is what you would end up designing for either material or girth or what kind of sizes you may need. Mostly, the biggest principle that's utilized is superposition, especially in force cases where you break it into components horizontally and vertically, and then you just add them together, which is the principle of superposition. But basically, you take the steps to do a diagram just like you would any other engineering science course, any other problem solving, and you have to establish your system. Are you doing X, Y, Z, or are you doing X, Y, Y, Z, etc., especially since once you start having your angles in there, things start turning negative. And so it's important to establish and label those first, as well as your loads and forces and how to resolve them. Like if you have a distributed load, resolve it into point loads. And then, of course, the centroid, which is always really important when establishing shear stress. So the picture at the top is an example of superposition, where it's broken down into Y and Z components, and then when you add them together, you get the shear distribution at the bottom picture there. And then this is just an example of an arbitrary beam with arbitrary loads on it, of how you would want to establish all of your attributes on your diagram.
Did you make that bottom diagram?
No.
Okay, because it's not consistent with the one above.
Right.
The one above has XZ, YZ is the face.
Exactly. And
Okay,
that's
all right.
because you can do them in whichever axis you want, like we've done.
Go ahead.
Bottom, basically we have these equations for unsymmetrical bending. Neutral axis location is important. You have the angle. It's really important for unsymmetrical bending because that's where all of your moments of inertia and all of your displacements are based off of, and so once you establish those, it's easier to calculate that shear stress. And then, of course, centroid, those equations we've used before, and then the parallel axis theorem, we've used this before for Ix and Iy, but now that we have unsymmetrical bending, we also need Ixy, or Ixy, which is that far right column over there, area times dx dy. And then utilizing that table, you plug into the shear stress equation down here at the bottom, utilizing the moments and the second moment area that you did in the table. So let's dive into an example. So I've got 3 examples. This first one is for force cause. The second one we'll go over is based off of the asymmetrical cross section, and the last one will be a combination of both. So example 1, this one's pretty simple. It's already broken down into 2 separate loads in the Z and the y-axis with the cross section shown, and of course we know how to make a distributed load a point load as it is over on the far right. And then the location right there, the locations on the cross-section right there are for later whenever we actually calculate the shear stress maximum tensile and compressive. So the force one is a lot easier than the cross-section. I can fit it all in one slide here. Once you break the moments down into components, it's pretty easy. Force times the distance, and then you have your z moment and y moment. Pretty easy. And then we of course know that the moment of inertia for a rectangular shape is bh cubed over 12, and so that's how we get our inertia in our x and y and z components. And then of course utilizing the simple equation for shear, moment times distance over inertia, we can get z shear and y shear. And then put a little turn off there. But once you convert this one into megapascals, it's 16.87. And then, I guess I left that part off. Then the numbers utilized for the distances, and the z was from the centroid, which we already know because it's since it is a simple rectangular shape, we know that it's in the center of the x and the y position. So we know that to the edge it'll be 0.05 meters in the y direction and 0.03 in the z. Okay, so the example 2 is over an asymmetrical cross section. This T-beam is not centered. It's got, it's all kinds of crazy shapes. We've got the top rectangle, which is 120 millimeters by 8, and the bottom, which is 80 by 8, and it's not on center. The center of the T is actually 32 millimeters from the left. So that makes it important to actually recalculate the centroid because it's not at the typical location for a T-beam. So we just use our equation that we've always used for finding a centroid, and we get that it's 66.4 millimeters from, and the way I calculated, I should precursor, is that the distances are based about point A. That way we can have that established as some kind of origin initially, and then from there we can move our axis to the centroid. And we got 18.4, 66.4 from A is where our centroid is at. So, on your slides you should be able to see the table. It shouldn't have been cut off. But we utilize that to calculate our ix, x, y, and xy. And then from there, we have to now use this equation to find the angle for the neutral axis. It's actually from the horizontal x-axis, that alpha, and that's where our neutral axis is now skewed because it is an asymmetrical cross-section. And you utilize that value, that equation. I have it typed out there, but there is the pretty version on the equation slide. And we utilize those numbers to not only complete the diagram, but also calculate our shear stress for tensile and compressive. So the maximum point should be about the bottom right corner and the top left corner, and utilize the equation again from the past slide where we have tangent alpha and our moments and our moments of
I was
inertia.
going to add something. One thing that might actually help you see that better is draw alpha.
Yeah, and I have it on the third example.
Yeah.
I meant to draw it on this one,
But on this one, if you draw it, then you can see it's the furthest point from alpha.
yes.
Right?
Yes, and that's
Like you
last slide.
said.
The last slide is really easy to see because, especially since it has both force and asymmetrical cross section, it's really hard to just guess.
Because they have no idea where the neutral axis is.
Right.
Right
It's,
now. But if you
16
drew it, then they'd say, oh, okay, now it makes sense.
Right, and it's 16 degrees from the x-axis, so it's a
It's
pretty
like
acute
that.
angle. Yeah.
Yeah.
It's a pretty acute
So it's
angle.
up here and down here.
So is it a line from A to essentially?
It goes through the centroid, and then it's at an angle, like she said,
Okay.
16
A's
degrees
alpha.
from X. So if you go like this, up 16 degrees, and then you measure from that this way.
Okay.
And that's one of the things that I was kind of disappointed in this diagram. I meant to draw over it, but because it's in 3D, it's hard to see. But on the next one, you'll see that everything is properly labeled.
Okay.
That's this diagram. So alpha in this case, because it is zy, alpha is from the left because z is positive to the left. And then obviously this is an angle section, and then the force is coming at an angle 10 degrees from the y-axis. And then we have to have this 3D of what the actual beam is because we need to calculate the moment later.
I bet I know where you got this one.
Maybe.
Advanced Strengths and Materials by Timoshenko,
I got it from
Kim-
a paper that actually worked out the solution for me. That way I could make sure I was.
I think that's right out of
The strength materials.
that Strengths and Materials book. Mm-hmm.
The centroid is again calculated from point A, so we know that it's 39.74 and 19.74. Again, pretty easy. Now we get into the complicated stuff. I'm keeping this diagram right here so you can see as we calculate with our table down here, we calculate our second moment areas right up there. And then we also have to calculate our moment, which we know from, I actually just took it from the steel manual, PAB over L, so it's 4 kilonewtons, which is what P is. I guess I forgot to mention that earlier. Times the span was 2 meters and 3 meters, over 5 was the total. And so that'll get you your moment, and then you just break that down into components, which is super easy because we know that that's negative 10 degrees. That should say negative 10, not positive 10, I'm so sorry. And those numbers would actually change because it is negative 10. It'd be my is negative 0.7. It's properly on the next slide. So those numbers crossed out. The proper ones are on the next slide. And then we utilize those again, just like we did with the last equation. It just takes some extra stuff because we have to break it down into components like we did with the force, but then also utilize our moment of inertia equations like we did previously. Sorry, I thought I heard a question.
Yeah. So is the 10 given in the problem statement? Or?
So basically the problem statement gives you this original theta right here.
Yeah. So
right, which is negative 10 degrees.
And why was
it that?
Negative?
It's negative because it's going that way versus that way.
Right hand rule.
Right hand rule, yeah. We have our...
Where's the
You
X?
got to make your fingers in the right direction.
Z-axis there.
You see
Okay.
Z.
Yeah, that's what threw me off too.
Gotcha.
So what happens when
Okay.
the z-axis is that way, it
Yeah.
makes a lot of negatives thrown in there later.
Okay.
And so that's why I had to follow along with the solution. We made a lot of mistakes at first.
Gotcha.
But then we may utilize that same equation, tangent alpha, to calculate and just like O'Hara said earlier, we have it just goes through our centroid and it's alpha from the z-axis, positive z-axis. So before our x-axis was positive that way, so our angle went this way, and that's why our neutral axis was like this. But of course now we have a different system. So that's 30.09 degrees, and then we just utilize that again in our equation with our moments and our second moment area theorem to calculate our maximum shear for tensile and compressive. And as you can see, our maximum tensile is at point A right down here, and our maximum compressive is at point B way up there. Does anybody have questions about which distances I use, moments, such and such? Yes,
Do you know where they use the y and z axis there?
So that comes down when you do it and come back to 3D. And so when you're looking at a beam, typically when you have the long ways, when you're looking at it this way is x and this way is y. So then when you take the cross section becomes a YZ system.
Typically.
And that's why before we didn't really need it because we didn't need to recalculate the moment, it was already given to us, so we could put it in the YZ system like this, with the z pointing out. Good question. That's great. Okay, so let's see. Yeah, that's all for that side, but 109 megapascals one way, negative 159 because it's compressive. And that's the end of the slides. Any questions?